Hi, I'm Kira.
I'm Ale.
And today, Ale is going to be explaining to me
Basics of optical setups and lasers, and basically the plans that we have for the laser illumination in our microscope.
the first step is safety. What you're going to want to do is firstly grab any one of these goggles. I was mistaken. We will be using solely the orange goggles today, just because they look cool.
Choosing the right goggle is very important, also because the lasers that we use are usually pretty high power, at least at the source. If you accidentally look directly into the laser, you can go blind, and that's probably not something you want. This guy is a laser. If I turn it on, this is what happens. You'll be able to see in a second that this is a blue laser of wavelength 444 nanometers. And so if you take a look what it does, it's very clear that you can see it, unless you use a filter, which is the glasses, and you're not gonna be able to see it as much. And so that's why we use this sort of thing, target, that is gonna basically absorb the light and emit also in different wavelength. And so even when you're wearing the glasses for your protection, you're still able to basically follow along where the laser is going. Right now, we have tried many different things over the past few days, and right now we're just testing how to couple the laser into a fiber. In general, if you want to really control where you're putting a laser beam, you need two mirrors that are at roughly 45 degrees, and you can basically adjust the position of the mirrors. You can go up, down with your laser, you can go sideways. This is a holder where you can put a fiber. You want to be at exactly the right angle and hitting the right spot in order to put all the light into the optical fiber. And then we're gonna use an optical fiber to basically guide the light into our turf platform where we are gonna have the sample. But before doing that, we need a way to pulse the laser, so like switch it on and off very fast. And we're gonna do that through an acousto-optical modulator, which is this guy right here. And then Kira is gonna show you how it works. Next up, we want to test this guy, which Kira knows it's an acousto-optical modulator.
Obviously.
Right? And you know how it works.
Of course. Of course.
Which
We
is-
all know how it works. Everyone knows how it works.
How it works. Mm-hmm. Right. Which is
Modulates the optics
with acoustics.
with acoustics.
Basically, this guy has a tiny crystal inside, and it's hooked up to this. This is a frequency driver, and this basically sends a radio frequency to this crystal, and the radio frequency makes the crystal vibrate. And by vibrating, if you have light going into the crystal at a particular angle and so on, this vibration is going to create diffraction pattern in the laser. And so basically, instead of having just laser light going straight through the crystal, it's gonna have basically a bunch of different laser beams that go into different directions, and that's gonna depend on how you modulate the vibration of the crystal and the angle of incidence and the size of your beam and all of that. And basically we want to have the maximum efficiency possible in deflecting this beam, so that, as you're gonna see soon, you're gonna always have some light that goes straight through, but you can get a good amount of light, like in optimized condition, up to 80% of the light that gets deflected. If you then block out the beam in the middle, but not the other beam that is deflected, you can use these as a switch on and off, because the only thing that you use is the deflected light.
What is it hitting? Or like what is it?
Whatever you want.
Okay.
So like if you just choose to couple your deflected light, you have that when you don't vibrate the crystal, you have zero light in the deflected
So it's
area.
going straight.
So it's all going straight,
Okay.
and we block it out.
Okay.
We don't care about that.
Okay.
But when we turn this on, then you get the deflected component. We can use that as our illumination source. The advantage of this is that we can switch on and off this guy very fast, like at the nanosecond level. And so this guy, through acoustics and everything, is basically a switch for your laser, on and off. Just because you only select the diffracted component, this is basically the way in which we can get like very high resolution in terms of timing.
What is the purpose of it to hit, like in the context of the quantum microscope?
The purpose of this is then we are going to select this light that is diffracted, couple it into an optical fiber, and connect the optical fiber to our sample stage. And so the light is then passed on to the sample stage, and it's gonna illuminate our sample. Illuminating our sample is what makes imaging possible.
Okay.
And what initiates all the quantum processes and everything. Microscopy works by illuminating our sample and then collecting some fluorescence and light that is a result of the illumination. You should be able to see, like right over there, a little spot going on and off. And that is basically what we're going to select in our experiments and take all the way to the sample. So we're gonna block the main part of the light. I'm gonna just select the smaller dot. We need to make a lot of adjustments and so on to maximize the signal that we can get in that second spot. It's not optimized whatsoever right now, but that is going to be how we create nanosecond laser pulses, thanks to Kira.
It's all me, guys.